Mr. Van. Yes. Is it recording? Excellent. Welcome to the Digital Signal Processing course, session 2. Okay, this is quite enough for students to attend the class. So if you please keep coming in every single week. We will be okay. A couple of things actually about the last session. I learned something. First thing I learned actually that we will postpone the deadline for the first exercise by 1 day. So deadline for the exercise 1 will be tomorrow. On online, it means 1 day after the original deadline. So first exercise deadline is postponed by 1 day. Oops. This one probably doesn't show up in the video, right? 1 day, only 1 day, okay? And basically because I learned something. So I was so fond of this slideshow which I made that didn't actually notice that it doesn't give the correct emphasis for different things. So I didn't pay too much attention on the most important thing was the sampling. Okay, so I will start this session by overviewing the sampling the other way around. And yeah, that was the second one. I will be turning these lectures a little bit more this way. So if you don't want to watch that one, will be just fine. You might actually want to come a little bit closer, although not closer than this line here. Okay, so more stuff on whiteboard. All right, good. Another thing, actually, the third point I would like to make is to make sure that you visit, say, this digital signal processing main page, say, frequently enough, at least once a week. This I will all the time add some stuff there. For example, now I already added some whiteboard pics. So it's basically a collection of whiteboard pics will be on our the Google Documents and under each session. So last time these whiteboard pics are actually right there. And there will be more whiteboard pictures today. Okay, that helps a little bit of following the stuff here. Then also another one, there's also a scoreboard. So fundamentally, these around 10 students have already returned the links to the exercises, and -1 means remember to share the link for commenting. All of those -1s actually means that you did not share the link by that anyone who has the link can comment. It's quite vital in order to get the feedback channel. I want to give you some hard time about you know what you have done there a little bit off. On the other hand, I might actually sometimes even give you positive feedback, but usually I just point out the points that need some fixing. Okay, so make sure you return exercise link, so that basically it's anyone, oops, one with link can comment. This is very important. Otherwise, you will miss the feedback. Okay. Another thing, I also noticed that the list, what I have there, the attendance list is somewhere there, and the names on the exercise didn't quite match. So if you haven't enrolled using Vinha, do it today at latest. Vinha was Ville, right? Not Vinha Vivi, but Vinha Ville. And this is Metropolia students. The other students, if you're not Metropolia or exchange student in Metropolia, then you should actually enroll using the link on the web page. Okay. Sometime tomorrow evening, I might start actually looking at their returns and start grading them. So please return the first exercise by tomorrow or tomorrow at some time. Okay. All right. Any questions? Let's go further. So today's topic is actually that signal fundamentals, but before going to that one, I will show you the last time stuff. Okay, where does it go? About signal fundamentals. Signal fundamentals, and especially there the sampling. How to do the sampling, and in MATLAB how you do the sampling, and I'll take just one slide here. So that's about this sampled signal, how it goes, say, in theory or mathematically. And this is how it actually, whoops, yeah, that's enough. So sampling. Oops. Oh, I cannot write anymore. Sampling. So sampling basically means that we have some sort of known signal. In real life, it is actually a signal that comes from the microphone or some to the sensor of some measurement system. When we are working with the MATLAB, most of the time in this course, the signal is actually something that we have generated ourselves. So that's why it's very important you can generate these the signal samples. And well, in real life, we have some time in seconds and then some value of the signal there. And an arbitrary signal might look something like that. They roughly sinusoid signal. In our case, it has some sort of functional form. So that's our x of t, which is the continuous time signal. Okay, then we have a couple of parameters like sampling rate or sample time. Sampling rate, I mark it usually with capital F and S, and the unit here is samples per second, or 1 over a second is the unit there. Samples per second or sample time or sampling time. Sample time is the time interval between two samples, and that's T of S. And unit is in seconds. Okay. Sample time basically means that we have these sample points in time okay? And it also ties the sampling with the index of the sampled signal and time. Okay. So those are the sample time vector actually. I'll mark it somewhere later. Okay, but anyways, the distance between those times are actually the TS, and there's also that the relationship with TS and FS, so that TS is 1 over FS and vice versa. Okay. Good. Then the samples. Someone said to me that the green doesn't show up. So I will be using green. So samples basically are just the values of the signal at those time values. Okay, right there. So if we have a functional form of x of t known, then the samples are simply x of n. N is our index, which also goes the same ways as the time, but that's a indexing vector, which is simply x, the continuous time signal at value n times ts. Okay, those are the points there. Okay. And then you can think of the computer. This is actually a vector or an array. If we have an index here, so this is basically the computer memory here. So in 1, 2, 3, 4, 5, 6, 7, 8, and so on. So this would be just x1, x2, x3, and so on. So those are just indexes on the table. Okay. And now the question, how to sample a sinusoid signal with some frequency fs. Just a moment, I'll just take a couple of pictures here. So I still remember. I need more space. Okay, sampling of the sinusoid. Whoa. This ain't good. This will make it such a big mess here. Sorry about that. Bad ink. Okay, so example. We have the sinusoid. X of t equals some amplitude times sine of 2 pi ft. Okay, so how to do the sampling? You know, okay, that f here is the signal frequency. All right. So the sampled signal x of n is simply, as it says there, x, the continuous time s, x times So we just use that equal to t a times sine 2 pi times, still the signal frequency is the same. There was a couple of returns which didn't have. So the signal frequency, the sampling rate actually went, you know, a little bit mixed up. And then we have n time ts. Okay. That's the time. Sample times. And there are several ways you can actually do this in MATLAB. For example, this is also the same as a times sine 2 pi f times, well, n times ts is also times n divided by fs. There. Then you can always say, okay, this is a vector t. Vector. How do your math teacher actually marks a variable as a vector? Okay, there's several kind of ways to do it. Have you seen a vector marking like, is this familiar? Vector? Yeah. So vector in here on signal processing is just same as a table. So this one here is table x or vector x. Same thing here. T is just the values n times ts. Right, which can start from 0 or actually also it can start like that. 0 is somewhere here and minus ts, minus 2 ts. So those are the sample times. Oops. So this is, for example, that way. You can compare, just replace the t vector as sample times 2 pi f times t vector. Right. Well, the same as here, but well, it's the vectorized times for sample. Okay, now I have given you enough of theory about it. Let's take a quick look. How does it go in MATLAB then? And yes, you will get easy points now, but anyways, my job here is not to entertain you. I'll do it in any ways that's free, but actually I try to teach you about the signal processing. So let's see, MATLAB. All right. Takes a while to start up. While we are starting, someone already have the MATLAB running. Let's see, MATLAB comments basically would be on blue color. Ah, there we go. Good. So sampling, oops, review. Okay, so system with a sampling rate of something, we can define the sampling rate, fs, for example. That sounds like a good sampling rate. Anything. So based on what kind of application are you running. That's a sampling rate for a very weird system. Then the sampling time is always 1 over fs. We might actually use either this or the other one. Okay. So either ts or 1 over fs. Anyways, it's the same thing. Sample time. Okay. Then we can do this several different ways. First of all, there's this amplitude. Well, I like to, go and fix the variables first, and then just start working with these symbols. So amplitude for that could be okay 0. That sounds like a good amplitude. There. Then the signal frequency, something that makes sense. Okay, I call it f sig, so it doesn't get mixed up with the sampling rate or anything like that. So signal frequency for that one, that's 300. So maybe something like, say, 50,000 hertz around. So this is the signal frequency for a sinusoid signal. All right. Now we have fundamentally almost everything here except the index vector. Okay. Somehow you need to define either the index vector. If you have an index vector, you can then use this n times ts. Okay. Or n divided by fs. Let's do that first and then take a look another way of doing it. Setting up the index vector is really good if you need to basically generate a small amount of data, small sequences that you would stem plot. That's actually handy there. But if you need long samples, then this is just extra step. For short data sequences, we could define the index vector, for example, from -2 to 20 or something like that. There. So then we can actually just plug those values into this formula. Hn equals a times sine of 2 pi f signal times index times ts. All right, so x1 equals to a times sine of 2 times pi times signal frequency times n vector times sampling time, like that. Okay, so this is the sample sign. All right, the same thing differently was like that. So we have n times ts replaced by n divided by fs is the same. Okay. Then, yeah, we could also then calculate the time vector tt, for example. That's n times ts, which is also exactly the same as, would be same as n divided by fs. Okay, so this is the time vector, the timetable. Okay, and use that one instead. So x3 equals a times sine of 2 pi f signal times t. That's the third way. Still the same. Does exactly the same thing. Okay. There are probably also some other methods. If you find a better one, please use it. How about a longer samples? Oops. Then we use the auto-indexing kind of thing with step size. For example, if we want samples from 0 seconds to say 3 seconds, and with that time step equals TS, then the sample times, this is different now, it's much longer. This far we have had only 23 or 4 samples, 24 samples, zeros included. 23, yeah, 23 samples. So now, okay, that's not a good one. It gets mixed up with the capital T's. Sample times, I'll just use TT2. Okay, sample time vector start from 0 with the time step of TS until 3 seconds. So this is 3 seconds long sample time vector at sampling rate of 32,000, no, 328,000 and so on sampling rate. Okay, so this is a long vector. So time sampling time vector. Which can be used again here. There. Okay. And that's 3 seconds long sample. Okay. I hope this clears up a little bit of the sampling things what you need to do on the exercise. Okay. Another thing, I will leave it more like a paper and pen exercise. Still, you need to fix this signal to noise ratio there for that noise, added noise. Just reminder about the added noise. Okay, let me take a quick look on the exercise first. Exercise 1. Did I ask about? Yes. Random noise with signal to noise ratio of SSS divided by 250. SSS was derived from your student ID number. That's the formula, or no, not the value, not the formula, it's the value. Okay, signal to noise ratio is always 10 times log of 10 of power of signal divided by power of noise, okay, which is the same as 20 times log 10 of the standard deviation of the signal divided by standard deviation of the noise. Okay, sigma, single sigma, not sigma squared. Okay, good. Remember that one when you're doing the 9th exercise. Okay. Any questions about this one? other than what? I cannot answer that what, but I will take a look over your shoulder when you are doing the nice exercise if you haven't done it yet. Yes, there's a question. Okay, it's part of the statistics. Yes. It basically says standard deviation is the root mean square difference of the signal to its mean. That's basically the definition of the standard deviation. No. Okay. Hey, we have a MATLAB. Standard deviation of something. Okay. How about STD of, oops, standard deviation of our signal x1. Yeah, it's a number. So signal, okay, that's a number which actually is the sigma of signal. Now we need to probably take a review the statistics. What is the formula for the standard deviation or the variance? Variance. So this is the STD. STD is just this one, and then the variance actually VAR in MATLAB is just a squared of that one, and I think the that goes something like this one minus x hat squared 1 over n. I think it's just a measure of how much the signal varies over the mean point. I think. Am I correct? Is there someone who can correct me? Standard deviation, does it have a... Oh, no. It was totally wrong. You know, there's n minus 1 here. Okay. So MATLAB actually also have quite nice reference on those functions. So it's square root of 1 over n minus 1. So this is basically, this is the root mean. Oh, no. This is the mean. This is the square part. So it's RMS is root mean square. Square is right there. Mean is right here. And root is right there. Root means square value of the signal. And it's the variance of the signal is directly proportional to the power of the signal. How much they are power on other than the DC component of the signal. Okay, good. Now we probably can go to today's stuff, unless you have more good questions. All right, just a couple of picks. Okay, exercise 1 was that one, and then I'm not going to do all the slideshow as the last time, but start with basically on that kind of slides. So fundamental, when we're talking about digital signal processing, that's the processing part on the slides. And processing just means that we will have some kind of operations on the system, and we can do a lot of things with only those 4 operations. So we have add, then we have scale, which means a product, scalar product, so we multiply with a constant value, which is also can be thought as again delay operation or time shift operation, and then is the multiplication of the signals. So mathematically add is just plus. If you subtract, then you just basically think of the subtraction as the addition of negative number. Okay, let me then give you an example of block diagram. Have you already been drawing some signal flow charts or block diagrams on some other course? Sometimes the discrete mathematics teacher goes through those. But anyways, it's quite, this is much simpler than the program flow charts, since we have less operations there. Okay. Block diagram of flow chart. On block diagram, this is actually a description of a system. Simple description of the system. Graphical description of the system. System implementation. Okay, it starts from left. There's the input signal X. Then I'll just write something here. A fundamental second order section. Then it has delay blocks. That's 1 step delay. It also can be marked as Z to -1, exactly the same thing. And then that's basically it. Then we can multiply this signal. Okay. Constant, whoops, wrong one. B0, B1, B2, and so on. So what does this system actually do this far? Well, if we have x of n here, then that point actually holds value of x of n -1, 1 time step delay. This point here has 1 time step delay of the previous one. So it's very simple. In here, we have B0 times x of n. Similarly, B1 times x of n -1. So basically, we just follow the signal flow, and we can say what does this system actually do for you. Then we have addition. Just for fun, I will add things here on this kind of section, and that starts to also explain about the why we call this system implementation, not just the formula what the system does, but this is the system implementation. Addition, in most of the processors, you can only add 2 values at a time. And here we have value, okay, b1 x of n minus 1 b1 x of n minus 1 plus b2 x of n minus 2. So this one here, if the system ended here, it would be b0 x of n plus b1 x of n minus 1 plus b2 x of n minus 2. Okay, so it does actually do some computing calculations of the input signal with the delays. And this starts to look like a filter. All right. It may also have a feedback term, same way as on, let's see, feedback. Is that familiar to you? Electronic students, are there any electronic students? Amplifiers, yes, amplifiers are based on negative feedback, right. Oscillators are based on positive feedback. The active filters are based on selective negative feedback, which is actually run by a certain phase shift to the positive input. All right. But output yn, if you need feedback, you cannot directly use that one since you are calculating it, the system is calculating it, but you have the previous value or previous values, okay. Delay, maybe 2 previous values like that one. And on amplifiers, when you're using negative feedback, you will just put a part of the signal back to the input to have the gain. Same thing here. You fundamentally put here another blocks for scaling the signal. So that would be after that a1 times yn minus 1 here. Or I'll just mark that one. a2 times yn minus 2. So it's feedback taken from the memory of the output. Okay. And then we sum it right here. And that gives you a way to calculate the output. And a system which has all of these operations is, well, it's a working linear system. Okay, and in this example, y of n here is just for fun, I will change the sign here. Okay, that's minus a1 minus a2. Since later on we'll use that kind of notation. Okay, we have this part coming on this end. Okay, we have b0 x of n plus b1 x of n minus 1 plus b2 x of n minus 2, and then we have minus a1 y n minus 1 minus a2 y n minus 2. Or, well, I mentioned also something about the negative feedback. Well, in principle, this is sort of negative feedback here. Just to make a reference to the analog electronics. On the other hand, this is nothing like in analog electronics. In golden 80s, which I have some vague memories about, there were actually some analog circuits, analog time shift circuits. So they took in an analog signal, sampled it, and then you could do discrete time systems with analog signals. Thank God we don't have those anymore. All right. Or was it the engineers who made fast enough signal processors? We don't need to care about the analog signal processing other than normal linear filtering and well, the sampling. Minimal amount of analog systems. Okay, so that's how it goes. The same way is actually the opposite way. So if we have a time-based representation, which is called a difference equation. So this one here is a difference equation. There is a difference equation for every single system, linear system. And for any difference equation, we can have multiple set of implementations. Okay. And this is the block diagram right there, or flow chart. And basically, if you have given a difference equation, then you can start drawing this system implementation, which is a block diagram. Why we don't just use this to calculate the values? I would give you a very good reason why not to use just the difference equation. You can, of course, just plug in that but basically what you can do is, since these are two blocks, block A and block B, or well, this is the A block and this is the B block. So we have signal x of n going first to block A and then go to block B, and then that's the output. On the other hand, for signal, it doesn't really care. If these systems are linear, then this is exactly the same result if we take first the block B and then block A. If they're linear, and they are. Okay, which means x of n actually comes to the plus, then it goes to the delays, then there's there's scaling, yeah, it gets messy. Then we have the another block is here, right? All right. What can you say about this signal here? Signal from this signal divided by 1 here, or this signal divided by 1 here. They equal. All right. So what we can do for the system is simplified quite remarkably. All right. Basically, the system fundamentally looks like this after the modification. And while this system uses uses 4 memory locations to store intermediate data. This uses just half of the amount, so half the memory requirement. Think of now a system which has, say, hundreds of points here. You really start saving some space, especially on small microcontrollers. Okay, so less memory required. And this is just one example why we need this implementation, flowcharts, okay, instead of just plugging everything in here on a formula. You really can start saving some resources. Okay. Here we have used only the 3 of those 4 symbols on block diagram. So we have addition, delay, scaling product. Then we have that 4th one, which is multiply, which is a signal multiply. And yes, we actually will use signal multiply at some point of this course. And basically, the signal multiply is the same as modulation. Modulation, same as signal multiply. Fundamentally, just an example how to modulate use amplitude modulation of a signal, how to generate an amplitude modulation signal. You basically just multiply. Okay. Sine, this would be sine modulation of a signal. So x of n times sine modulation frequency times n times ts. Nothing fancy about it, other than, well, in MATLAB you need to do dot multiplication. Now that will be actually then, this modulation frequency is the carrier frequency, and then the signal actually gives the envelope for the data. Okay. So if we had a x of n, say something like that, sine modulation frequency, well, that's kind of dull, boring. So this modulated signal would follow the envelope of the original, except, well, it follows it like that. So that's amplitude modulated signal. Okay. And yes, we will have some exercises later on this course about the modulation. Good. So we have those 4 simple operators, and that's enough most of the time. Okay. More stuff. And this gets heavy. System has some fundamental properties, and those are the 4 most important properties. Linearity of the system. Okay, system properties. Linear. If a system is linear, then we can apply superposition principle. That system is not linear. Okay. Fundamentally, what does it actually mean? That if we have a system consisting of, okay, x of n, y of n, this system is, wait a minute, type of system that is linear, then you can actually run 2 signals here. Oops, not x1 plus x2. So these are 2 different signals. If this is actually the system function, whatever it does, system function is always like that. Then if the system is linear, then if you have this just sum of the signals, then the output would be the sum of individual signals. Okay, that's the first part. So it's additive system. You can then basically calculate the output as separate outputs, but only if the system is linear. For example, if a system does some clipping of the data, for example, if I talk too loud to this audio, it will start saturating. If the system saturates, you cannot add any more into the signal, or you can try, but it doesn't come out. It still saturates. Then basically it's a clipping system is non-linear system. Okay. Same actually, it's also on linear systems. You can have scaling factors, say A and B here. If the system is linear, oops, then the scaling can be taken out of this equation. So basically, if you multiply a signal, say c times x of n goes in, then basically after the system, yn should be also c times whatever the system input was, or the output was before the scaling. Okay, simple but very important factor. So this actually states that you can turn up the amplification of the signal either here or on the other side. And again, well, this microphone kind of thing is never totally linear in mathematical sense. Okay. Second important property of the signal would be causality, not casuality. Causal. Okay, what does it say? There is no effect before action. It means that the system doesn't forecast the future. So it does not do for good example of a non-causal system is human being. Human beings always, tend to look after what happens if. Okay, the causal system doesn't know anything about the future. It cannot do any forecasts, even the worst ones. Okay, so it means that so it does not forecast. And another one, actually, it's the effect of a signal starts at the same time of the signal or later. All right, so causal. Well, most of the natural signals systems are causal. On electronics, of course, or digital, you can make also non-causal signals, since in sense you know the future if you are post-processing the data. When you're processing this point, you can go either positive or negative indexes to check the data. Okay, causal. No action before reaction. Stable. Or stability, actually. Stable. A system is stable if, okay, this is a definition kind of thing. This is also called bounded input, bounded output stability. Bounded input, bounded output stability. So bounded input actually causes always the bounded output. So on systems, a good audio system is a bipole-stable system. So if we think if the microphone levels, say between plus minus 200 millivolts, you design a system, analog system, such that the gain and the addition to the system, or the reference point of the system, will take that data, and that's the 0 digit, and that's the basically A to D converter, the maximum value. These are the bounded input. If that one stays here, then the bounded output would mean simply that the gain and the lever shifting has been designed so that it actually fills the A to D conversion range. Easy. Okay. Uh, they are actually on say a digital system is easy to cause unbounded output. One sure thing is division is very dangerous operation in discrete math. You can divide by 0 or divide by very small number, you get huge number you didn't expect, the rest of the system didn't expect. Okay, so basically stability is one very important to check from the system. But there are some tools. There are some simple tools to make sure that here a filter is stable. Okay. Third one is time shift fourth property is time shift invariance. Right, time shift invariance, meaning that the system properties do not change by time. Fundamentally, it's the same as the static. So if you have a website that does every single time the same thing, then it will be a static website, right? But if it has some changing components, then it's dynamic. And then it's not time shift invariant anymore. So this actually means on this system wise, if you have a system like that and you apply time shift for the input, okay, that was the f of x of n, right? Set time shift by n values, what comes out should be fundamentally, well, this is just a formula here, should be basically exactly the same as x of n, but I mark it like this, delayed by n steps. So just exactly the same output, but later on for the same delayed signal. Okay, so good example, parking meter on daytime. But parking meter on evening, it's not that like that, and that's good thing. Otherwise, at the middle of the night, you need to put some more coins on it. Okay, daytime, yes. Nighttime, no. Overall, no. All right, those 4 properties. Yep, some same things on the difference equations. We have an example of 4-point average filter. Okay, maybe we'll take a closer look on that one. Block diagrams, so basically the same thing I already had there. Okay. I'll take more pictures. I need an automatic camera right there and there. Does anyone need a innovation project? Couple of cameras, automatic, saving of the pictures when they are done. Okay, system properties. The beginning of today's exercise actually is about the system properties of these four very important fundamentals. Okay. Let's see what I'll say. Transfer function. Have you heard about transfer function? Yes, some of you, especially on electronics. Transfer function is the function of what you get by Laplace transforming something, and that goes ugly there. It's equally ugly here, but you cannot make omelette without breaking the eggs, right? Or maybe you can, but then it's not omelette anymore. Transfer function. The system transfer function, okay. Take a quick look. What did I have there? Block diagrams. Basically, it's a function that describes the system in complex spectrum, and that's a little bit of hard to try to understand. Okay. In spectral space, you can actually divide this system in sinusoid as a series of sinusoid functions. It's periodic, but what does it have to do with this transfer function? Basically, everything falls back into so-called convolution theorem, where you basically multiply the system input in frequency space with a transfer function, and that gives you the frequency space out. Okay. On continuous time systems, that's how it goes. So it's a Laplace transfer of output divided by Laplace transfer of input. That's a definition. On discrete time signals, on discrete time systems, we have the definition for the transfer function. It's basically quite ugly. It's the so-called Z transform of y of n divided by Z transform of x of n. What? Okay. Does it make any sense? I hope to make some sense to it. So fundamentally it says that the output of a system, the Z transform of output of the system, is the same as the transfer function times Z transform of the x of n. Okay, and this transfer is just a generalization of Fourier transform. On the other hand, I'm not writing it down, since otherwise mathematicians would come and, burn me on a pile of physics books. Mathematicians and physicists have been, had a kind of friendly competition of who invented what and what is the philosophy of things. For mathematics, basically the philosophy is mathematics, and you cannot touch the sacred philosophy. For physics, we just take and quick squeeze the mathematics until it's usable. Okay, and that's the engineering way of doing things. Yeah, just use it. Don't think too much of the philosophy of the things. Use the tools. Okay. I try to make some sense out of this. Okay, for example, if a system transfer function, now remember it's in frequency space. If a system transfer function is specially, okay, just prime, the amplitude part of system, since it's complex, okay, but then it's also in spectral space. So that's fundamentally, there is some frequency. Frequency. For example, if it looks something like this, cutoff frequency. Okay, so this is low pass filter. It blocks the higher frequency components from the signal. If the system transfer function was such that the amplitude response of the system looks like this, then it starts to make sense. Then you just think, okay, it's just a Z transform of the input. You multiply it with this one, you get output, the Z transform of the output. And actually, it just appears that the Z transform is also a linear operation. So if you have a linear system, you get X of n in and Y of n out. Basically, the same applies also for Z transform. This might actually look quite similar to the S transform and analog signals if you have taken that kind of course. And that one here, the function is defined by the transfer function. And there's not much magic about it. Okay. Because of those properties there, transfer function, some important Z transform properties. One that is linear transform, then another one is time shift. If you have time shift of signal, it actually comes out as Z to minus or the time shift. Then unit impulse actually transforms into 1 and unit step as Z divided by 1 plus Z. Okay. Think of a system with a difference equation. We know the difference equation. If we know this, for example, that block diagram what I had there, the example block diagram. Right, so we have the difference equation y of n equals b0 times x of n plus b1, x of n minus 1 plus b2 x of n minus 2 minus a1 times y n minus 1 plus a2 times y n minus 2. Okay, by magic you can actually turn basically, well, it's mathematics done by a physicist. Okay, that goes on the other side here. Now it makes a little bit more sense to have the minus sign here. So in here you have y of n plus a1 times y of n minus 1 plus b1 a2 y n minus 2 equals to that one, b0 and so on. Then the time shift operation. If you do the Z transform of both sides, you still have the same equation there. It's linear means that the equation equal sign remains. You end up having actually y of n. Okay, I will just start making it a little bit y of n plus, that goes out because it's the linear operation a1 z y of n minus 1, but there's also time shift operation times z to minus 1 plus a2 z transform of y of n times z to minus 2 equals to whatever comes out of there, which means that the transfer function is this divided by that x of n part times b0, which means that you can actually, if you have the, if you know the difference equation, then in this example you have on the numerator, you have b0 plus b1 z to minus 1 plus b2 z to minus 2, 1 plus a1 z to minus 1 plus a2 z to minus 2. So basically what we have here, wait a minute, we have exactly the same parameters as in difference equation. Okay, on both, okay, 1 times numerator and denominator. So basically you need to know only the difference equation or transfer function. You can then, those are the same system parameters for both. Okay. And moreover, this is a nice, it's basically a rational polynomial of z to minus 1. Okay. Which means that we just use the equation, start calculating some things about it. Wow. Okay. These values actually, if we had a general kind of difference equation, we could then derive the system parameters. I think I'll do it there just for fun. Just for the fun of it. Is it so much fun? No. All right. Difference equation. Say generic form or general form of a difference equation is you have a sum of something ai times, well, let me use k here, y n minus k starting from 0 to some number n equals to sum of k from 0 to n again, b kx n minus k. Okay, that's a general form of difference equation of linear time invariant system. Linear time shift invariant. I don't know if it's causal yet, and I don't know if it's stable yet. Okay, Fundamentally, it is causal if B0, or actually, let's see, there are more non-zero scaling factors on input on the beginning or before the first non-zero digit of the output. Okay. Okay, that's the general form. And well, just comparing here, h of z, I had b0, 1, 2, 1, which was just this scaling factor. And I did do some magic here. Okay, then the transfer function, the same thing. For, and that's general form, and for linear time invariant systems. Those will produce z2 minus k. Same here. The time shift actually produces that one. All the scaling factors come out. And comparing that one, h of z, the transfer function, is simply k from 0 to n be k times z2 minus k divided by sum of ak z2 minus k. Okay. Still general form. Then you can actually do a little bit further. Fundamentally, this will end up being a positive exponent power of z's here. Just multiply, divider and dividend by z to n. Actually, what you get is something like this. B0 times z to n plus b1 z to n minus 1 plus, and so on, and then the last term is bn divided by a0 z to n plus a1 z to n minus 1 plus, and so on, and ok, that's a complex polynomial. So what makes it complex? Nothing yet, just that we do not take account every single root what it has. On simple mathematics, square root of 2, if it goes negative, you say, okay, there's no what is that point? Special point for that function. Okay. But this is a complex polynomial and it has roots. So that same polynomial can be actually expressed so that there's a scaling factor times z minus the special point, the roots from 1 to n, and the product of the roots minus k. All right, now we basically have all what we need. That's the general form, and this is the same polynomial as the product form k. Now we can go and say, all right, now we can calculate this special point of this transfer function called poles and zeros. Okay. So the poles, or actually 0 points, are basically the roots zk on that formula of the numerator polynomial. And poles is basically roots pk of denominator or divisor. Hard stuff. On analog systems, the stability criteria was that the roots are on where? Hey, you know, right? Which side? Yeah, then it's stable, yes. Negative poles. And here we have discrete time system. It's totally different. The location of poles actually now tell you if the system is stable or not. All poles, basically, the norm of that poles is less than 1. Then it's stable system. Okay. Another thing what we can do with the zeros and poles, we can plot them. So-called Aragon's diagram. Which is simply 0 pole plot in complex plane. An example. So that's the whole thing. Now we just need to add some information. So this here is the unit circle in complex plane. This is real axis, imaginary axis. Remember, this is just complex numbers. Don't worry about the philosophy of complex numbers. They don't have any philosophy. We just need these complex numbers because of the phase of the signal or phase shift of the system. Okay, we need those. So if our zeros would be basically blue ones, zeros, sometimes they will be on the unit circle, sometimes not. They can also be something like that here, anywhere. But only so that you also have the complex conjugate pair. Then poles. Okay. Poles inside of the unit circle, maybe some multiple poles and even some poles on the origin. Okay, just an example. So that would be stable. Stable system. Okay, if a system is unstable, it usually starts saturating really fast. So stability criteria is a very good criteria of a system. It's kind of does it make sense test. For filters, it's crucial to have them stable. The zeros can be anywhere, practically anywhere. They can be even 2 miles that way, and it's still the same. It doesn't affect on the stability. The poles do have the effect on the stability. Wow. Excellent. So that is my show. And we will start the exercises about 10 past 12. Okay, so thank you. Unless you have some questions. Yes, you are dismissed now, so you can go and explode your head now. Okay, that's all.